Yeah, in economics, the Lagrangian functions, sometimes called Lagrange multiplier method, LLM. It is actually the method that is dealing up with constraint optimization. For example, we can actually say find the maximum or minimum of the following function fxy subject to gxy is equal to c. We should find the possible solution for this particular statement. So we have got three steps that are used. First of all, you write the expression in a Lagrange multiplier function as follows: L bracket x comma y is equal to fx comma y minus lambda, and when you put lambda, you actually say gx comma y minus c. So you can actually see that I have taken a different approach on that one. So here, this is that, and this is this particular part, and then you just put a lambda at that particular moment, and then where in this case where lambda is a constant, so lambda is a constant, and then the second point, having obtained that, you actually differentiate. Okay, you differentiate L with respect to x, and after that you equate the expression into 0, and this expression that you get is a partial function that you get, because it has some element of the other function. Now the third part, you differentiate again L with respect to y, and when you differentiate that one with respect to y, you again equate the expression to 0 again, and then thereafter you just now put number 3, this particular statement, gxy is equal to c. So you actually solve that part. Then in this case, it shows that you have got simultaneous equations, and there are 4. This is there are actually 3. This is the first one, this is the second one, and this is the third one. Then thereafter, you actually now solve the simultaneous equation for x, y, and the lambda. And once you do that, you actually you can be able to solve the statement. So normally, what happens is that if we look at now the connotation, fx y can be any function. Fxy can be any function. For example, it can be maybe a Lagrangian function, which we were discussing previously, like it can be like a function which can be like that, or it can be a quadratic function which can be like this, or it can be any linear function which you can actually can have, and all those factors, or it can be like a joint function xy. So this is now the rule of the that you must be able to take note of. And normally the subject to part, which is actually the constrained part, which is an objective function, it can be a linear function of this particular sort, maybe is equal to 24, or it can be any linear function which can be as linear as that. So at the end, we are able to actually determine the value in that on that particular level. Now, so let's look at the following, just to quickly apply the context and then determine the value. This time around, we should be able to have like a Cobb-Douglas function, which is equal to u bracket x comma y is equal to a x to the power a y to the power b, and which is actually subject to px plus qy is equal to m, where in this case capital A, B, P, and the Q and the M in this case are positive constant, positive constant. So we can actually find the maximum of this particular expression yb subject to like px plus qy is equal to m. So looking at it, number one, we should be able to represent it in a Lagrange multiplier function, which is equal to axa yb, and then this is equal to lambda bracket px plus qy minus m in this case. So this is equal to 0. So you actually take that one as a Lagrangian function. So then I should be able to get when x is equal to 1, what is this part when x is equal to 1. So in this case I'll have I'll have a function which is equal to a. I'm only concentrated at a, so it can be yb, and then this one I'll concentrate where there is again x, because I'm differentiating x. So in this case I would only have lambda p, then this is equal to 0. Then if I take the second one, I'll be able to differentiate it with respect to the other one, so, with respect to y. Then for that one I'll be able to have b and the a x to the power a y b minus 1. So it will be like that, and then it will be minus lambda q, like that, then is equal to 0. So here lambda q is coming in because you are multiplying it is like lambda px minus lambda q y minus lambda m. So if you are differentiating with respect to y, this is a constant, that is a constant, because maybe y. Therefore, what is remaining is this one, which has y. So if you are differentiating y in this case, since it's just y, that's why it is becoming like this one. That's why we are taking it to that. And then in the third function, in that case, is equal to the constant, which is equal to px plus qy is equal to m. So this is equation 1, this is equation 2, and this is equation 3. So having done that, then you must be able to solve for lambda. You must be able to solve for lambda. So in this case, I can say lambda is equal to a x a minus 1 yb over p, which is equal to again b a x a y b minus 1 over q. So that is actually the value of lambda. So you should be able now to actually when you continue cancelling, you should be able to find that ay over p is the same as bx over q, is the same as bx over q. So that from that particular point, you must now be able to solve for qi. What is qi? And in terms of the other values, so that you can establish what particular value is all about, and then thereafter you must try to solve for x and solve for y. So I will leave this other part for you to actually practice so that you can determine the values. So that's actually how we look at these particular problems. We are going to continue with more examples in the next session on this, so that after that you can actually now practice to see how we can actually take on board. Thank you.